Good morning. In this section, we study sequences. A sequence is an ordered list of elements. Sequences are important to computing because of the iterative nature of computing programs. The time complexity of recursive functions and for loops are computed by means of sequences and summations. Sequences. Definition 1. A sequence is a function from a subset of the set of integers, usually either the set 0, 1, 2 or the set 1, 2, 3, to a set S. We use the notation a subscript n to denote the image of the integer n. We call a subscript n a term in the sequence. We use the notation the set containing a subscript n to describe the sequence. Consider the sequence the set a subscript n, where a subscript n is equal to 1 over n. List the first four terms of the sequence denoted a1, a2, a3, and a4. They are 1, 1/2, 1/3, and 1/4. Definition 2. A geometric progression is a sequence of the form a, ar squared, dot, 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 ar to the n, dot, dot, dot. Remark. A geometric progression is a discrete analog of the exponential function f of x is equal to ar to the x power. Example 2.1. Consider the sequence bn, where b subscript n is equal to -1 to the n power. List the first four terms of the sequence to denote b0, b1, b2, and b3. b0 is equal to 1, b1 is equal to -1, b2 is equal to 1, and b3 is equal to -1. Please note that the odd numbers powers produce -1 and the even numbers powers produce +1. Example 2.2. Consider the sequence c subscript n, where cn is equal to 2 times 5 to the n. List the first four terms of the sequence denoted, and I haven't got this right here, c sub 0, c sub 1, c sub 2, and c sub 3. Solution. C sub 0 is equal to 2, c sub 1 is equal to 10, c sub 2 is equal to 50, and c sub 3 is equal to 250. Consider the sequence b sub n, where b sub n is equal to 6 times 1/3 to the n power. List the first four terms of the sequence denoted b0, b1, and b3. Well, again, I haven't got the right letter, so b0 is equal to 6, b subscript 1 is equal to 2, b subscript 2 is equal to 2/3, and b subscript 3 is equal to 2/9. Definition 3. An arithmetic progression is a sequence of the form a plus d, a plus 2d, and so on until we get to a plus nd, where the initial term a and the common difference d are real numbers. An arithmetic progression is a discrete analog of the linear function f of x is equal to dx plus a. Example 3.1. Consider the sequence Sn, where Sn is equal to -1 plus 4n. List the first four terms of the sequence denoted S0, S1, S2, and S3. S0 is equal to -1, S1 is equal to 3, S2 is equal to 7, and S3 is equal to 11. Consider the sequence Tn, where Tn is equal to 7 minus 3n, and find the first four terms of the sequence. T0 is equal to 7, T1 is equal to 4, T2 is equal to 1, and T3 is equal to -2. Example 4. The string ABCD is a string of length 4. Recurrence relations. Another way to specify a sequence is to provide one or more initial terms together with a rule for determining the subsequent terms from those that precede them. Recurrence relations are very important in computing because we generally describe complexity with recurrence relations, and we have recursive functions that are described with recurrent relations. So this is a very important section of our course here. Definition 4. A recurrence relation for the sequence A sub n is an equation that expresses A sub n in terms of one or more of the previous terms of the sequence, namely A0, A1 through an-1, for all integers with n, all integers n with n greater than or equal to n sub 0, where n sub 0 is a non-negative integer. A sequence is called a solution of a recurrence relation if its terms satisfy the recurrence relation. A recurrence relation is said to recursively define a sequence. We will explain this alternative terminology in Chapter 5. Example 5. Let A sub n be the sequence that satisfies the recurrence relation A sub n is equal to A sub n minus 1 plus 3 for n equal 1, 2, 3, and suppose that A sub 0 is equal to 2. What are A sub 1, A sub 2, and A sub 3? Solution. We see from the recurrence relation that A sub 1 is equal to A sub 0 plus 3 is equal to 2 plus 3 is equal to 5. It follows then that A sub 2 is equal to A sub 1 plus 3 is equal to 5 plus 3 is equal to 8, and A sub 3 is 8 plus 3 is equal to 11. I may remark here that Excel is an ideal tool for solving these kinds of exercises. I've excerpted a worksheet below. I put I, the integer values for A sub n, and then A sub I serves as, or A subscript I is how we do it in computer programming, enclosing our subscript in square brackets. And then I'm able to find various values just by computing the first one or computing the second one based on the first one, and then just moving my cursor over the value column to compute the remaining values. Example 6. Let A sub n be a sequence that satisfies the recurrence relation A sub n equal A sub n minus 1 minus A sub n minus 2 for n equal 2, 3, 4, and so on. And suppose we have A sub 0 equal 3 and A sub 1 equal 5. What are A sub 2 and A sub 3? Solution. We see from the recurrence relation that A sub 2 is equal to A sub 1 minus A sub 0, 5 minus 3 equal 2. It then follows that A sub 3 equal 2 minus 5 is equal to minus 3. We can find A sub 4 and A sub 5 and each successive term in a similar way as shown below. Definition 5. The Fibonacci sequence, F0, F1, F2, and so on, is defined by the initial conditions F0 equals 0 and F1 equal 1, and the recurrence relation F sub n is equal to F sub n minus 1 plus F sub n minus 2 for n equal 2, 3, 4, and so on. Example 7. Find the Fibonacci numbers F2, 3, 4, 5, and 6. Solution. The recurrence relation for the Fibonacci sequence tells us that we find successive terms by adding the previous two terms. Because the initial conditions tell us that F0 is equal to 0 and F1 is equal to 1, using the recurrence relation in the definition, we find that F2 is equal to 1, F3 is equal to 2, F4 is equal to 3, F5 is equal to 5, and F6 is equal to 8. As in our previous recurrence relations, we can employ Excel to find the values of the desired terms, as I have shown in this slide. Example 8. Suppose that an is a sequence of integers defined by a sub n equal n factorial. The value of the factorial function at the integer n, where n equals 1, 2, 3, I think that's n equals 1, 2, 3, and so on, because n factorial equal n times n minus 1 times n minus 2, down to 2 times 1, equals n times n minus 1 factorial equals n times a to the n minus 1. We see that the sequence of factorials satisfies the recurrence relation a sub n is equal to n times a to the n minus 1 together with the initial conditions a sub 1 equal 1. 9.1. Example. Determine whether the sequence a sub n, where a sub n equal 3n, for every non-negative integer n, is a solution of the recurrence relation a sub n is equal to 2a sub n minus 1 minus a sub n minus 2 for n equal 2, 3, 4. Solution, suppose that a sub n equal 3 sub n for every non-negative integer n. Then for n greater than or equal to 2, we see that 2a sub n minus 1 minus a sub n minus 2 is equal to 2 times the quantity 3 times the quantity n minus 1 minus 3 times the quantity n minus 2 is equal to 3n is equal to a sub n. Therefore, a sub n, where a sub n equal 3n, is a solution of the recurrence relation. Example 9.2. Determine whether the sequence where a sub n equal 2 to the n for every non-negative integer n is a solution to the recurrence relation a sub n equal 2a to the n minus 1 minus a to the n minus 2 for n equal 2, 3, 4. Suppose that a sub n equal 2 to the n for every non-negative integer n. Note that a sub 0 equal 1, and a sub 1 equal 2, and a sub 2 equal 4. Because 2a sub 1 minus a sub 0 equal 2 times 2 minus 1 equal 3, which is not equal to a sub 2, we see that a sub n, where a sub n equal 2 to the n, is not a solution of the recurrence relation. Determine whether the sequence a sub n, where a sub n is equal to the constant 5 for every non-negative integer n, is a solution of the recurrence relation a sub n equal 2a sub n minus 1 minus a sub n minus 2 for n equal 2, 3, 4. Suppose that a sub n is equal to 5 for every non-negative integer n. Then for n greater than or equal to 2, we see that 2a sub n minus 1 minus a sub n minus 2 is 2 times 5 minus 5 is equal to 5, which is equal to a sub n. Therefore, a sub n, where a sub n equal 5, is a solution of the recurrence relation. Example 10. We are going to use example 10 here and in our exercises and in the next module when we do time complexity. Example 10. Solve the recurrence relation and initial conditions in example 5. Recall the recurrence relation in example 5. A sub n equal a sub n minus 1 plus 3 for n equal 2, 3, 4, and suppose that a sub 1 equal 2. We can successively apply the recurrence relation in example 5, starting with the initial condition a sub 1 equal 2 and working upward until we reach a sub n to deduce a closed formula for the sequence. We see that a sub 2 equal 2 plus 3, a sub 3 is equal to 2 plus 3 plus 3 is equal to 2 plus 3 times 2, a sub 4 is equal to 2 plus 2 times 3 plus 3 is equal to 2 plus 3 times 3, and finally a sub n is equal to a sub n minus 1 plus 3 is equal to 2 plus 3 times n minus 2 plus 3, which is equal to 2 plus 3 times n minus 1. And we have found our closed form representation, or non-recurrent form. We can also successfully apply the recurrence relation in example 5, starting with the term a sub n and working downward until we reach the initial conditions. A sub n is equal to a sub n minus 1 plus 3, a sub n minus 2 plus 3, which is a sub n minus 2 plus 3 times 2. A sub n minus 4 plus 3 is plus 3 times 3 is a sub n minus 4 plus 4 times 3. And all the way down to a sub 2 is equal to 2 plus 3 times n minus 1.